Hello everyone, welcome back to another lecture for ECE 2021. Today we're going to look at a bit on soldering and soldering techniques. Unfortunately, unless you have these tools at home, this is not something you're going to get to try this term, but let's have a quick look at some of the pieces here. One of the things that's really important when you're soldering is a means of holding things steady. So I have a little electronic vise here. It's adjustable into all kinds of different positions, so I can clamp whether it be wires or circuit boards. Okay, clearly I have my solder. I've got a couple of different types here. This is a fairly fine solder, whereas this one's a little bit thicker. If I can find the end of it. So you see this solder is a little thicker. This choice of solder just kind of depends on the size of the items you might be soldering. Let's come back and talk about the solder here again in a second. Tweezers for holding some of your small pieces. Okay. A magnifying loupe. It can be hard to inspect your solder joints without one, so it's nice to have one of those on hand. A set of side cutters can also be used as wire strippers as well, although I do have specific wire strippers. Personally, I actually don't use wire strippers much. I generally just strip with the wire cutters. Safety glasses are always important to make sure you're not getting a piece of solder or something flying in your eyes. And of course the soldering iron itself. This particular soldering iron is part of a soldering station. If I could bring the soldering station into view here, this is a soldering station. This is a fairly inexpensive brand. This is made by circuit specialists, but it has this. When you have this large base, this type of soldering iron that's connected to a station has much quicker heating times and recovers much quicker if you're soldering large things that tend to draw the heat away. Okay, so it's nice to have a soldering station, and you can buy ones like these fairly inexpensively. You can get them online for probably $40 or $50, whereas a more high-end soldering station like a Weller, which is very well known, might be $200 or $300. Okay, so with the soldering iron, I also have my base to hold the iron, and you'll notice I have a sponge here, a wet sponge that we're going to talk about, necessary for keeping your tip clean. Some solder stations, instead of the wet sponge, will use a type of steel wool for cleaning your tip. Okay. Some of the other things that we'll come back to visit a little bit more later on. Here is solder braid. This is a means of desoldering things. Here's a slightly larger type of solder braid. Some other things, flux pen. This helps clean the area and helps with conduction of the heat. Something that we're not really going to show today, but this is a solder paste in a syringe that can allow you to apply this paste that's in liquid form right now, and through a heating, some form of kind of heat over the entire surface, you can solder many solder joints at once. Okay, let's clean up this area for a second, and we'll come back and look at a little more detail at some of the pieces. Okay, so just cleaned up my workspace. put on my safety glasses, and let's have a look at the solder itself here for a second. If we zoom in here on the top of this, we'll note some information on the top of this spool of solder here, and you'll see the diameter of the solder, 0.5 millimeters. Again, the size, maybe you can't see the point there, but the size will be kind of dependent on the kind of precision of soldering that you're doing. But what I want you to focus on here again is these numbers here. So what this is saying is that this is SN for tin, 63%, and PB is for lead, 37%. And there's been a large movement to get away from lead in our components, so you can get lead-free brands, and we'll come back to talk about that in a second. Also here, you'll notice that this says it has a rosin core. Okay, so my flux pen here that I said is used to clean your area and help with the conduction, thermal conduction. This is rosin, and rosin's heavily used in soldering to keep your area clean and help with heat transfer. Okay, if I just focusing on the properties of the solder here for a second. Kester is a popular brand of solder. If we look here, we'll notice that you can get kind of a cheaper, possibly less expensive solder, but fairly common, is 60% tin, 40% lead, but it has a slightly higher melting point, whereas the 63-37 ratio has one of the lowest melting points of solder and can make for easier soldering. Now we see that there are some with lower melting points, but these are a little bit more exotic and a little bit more rare, and you'll see that some of these are only available in a paste, not in the wire form that we're looking at here today. You'll see that there are many lead-free options, but note that the melting point for all of these is much higher. So to go lead-free presents some additional challenges when soldering, because you have to get your joints, your conductors hotter, your solder joints hotter, in order to get a good solder flow and a good solder connection. Okay, we come back here to our camera. One of the other really important things when we're soldering is making sure we keep the tip clean of our soldering iron. Okay, so if we have a look at this tip right now, it's relatively clean, but it's important that you keep it clean throughout. As the rosin in the solder melts on that, you tend to get a buildup of rosin, and you can sometimes have a buildup of solder, and will affect the heat transfer and make it more difficult to solder. And this is one of the biggest issues that inexperienced people face when soldering, is not keeping the tip clean. So if you have a soldering iron or station that came with a sponge, you get this sponge wet. I don't know if you can see the water in there, so I've got that pretty soaking wet, and I just try to rub around the tip to get it clean. And now you might notice that the tip is a little bit shiny. That's what we're hoping to see. One of the other things we do to help with heat transfer is we tin the tip. So we just take a bit of solder and we melt it on the tip and try to get a nice coating over the surface of that tip. Okay, so you'll see the solder melting in there, and we'll clean it again to make sure that there's no excess solder on there. Okay, so now we have a nice shiny soldering iron tip. The other thing I guess I didn't show here, you might have noted when I showed the soldering station here, is the temperature we're set at. It's a little bit hard for you to see here, but the dial is turned right here. Maybe I can zoom out here a little bit to show that a little bit easier. Okay, so right here I'm pointing somewhere between 350 and 400 degrees, probably right around 375. I find that a nice area to solder. It's low enough that you have to hold the soldering iron on a circuit board for a relatively long length of time to do damage, but it's hot enough to get good flow of your solder and pretty good productivity with your soldering. Sometimes if you have very large surfaces, very large thermally conductive surfaces, you may need to turn the iron up just to get that surface hot enough so that you get good flow. Okay, so one of the first things that I like to show soldering, and you might think is trivial, is soldering a wire. So I've just taken a chunk of wire here, I've cut off, and first thing we're going to need to do is expose the copper of that wire. It still has an insulation on it. Again, I often will, I'm just going to make a clean cut here. I'll often just use the side cutters for stripping the wire, and this is a little bit of a learned technique. Just try to cut in just through the insulation and pull that insulation off. Okay, again, this is a little bit of a learned technique, so until you're familiar with it, that may be a little bit more challenging. Now this is what we call a stranded wire, right? So we can see that the wire has multiple strands. Maybe let me zoom in here a little bit more. Okay, so we can see multiple strands to that wire, and it can make a bit of a mess when you try to solder it with those strands all free. So I typically will twist those strands together if I'm using stranded wire. If I have solid wire, then as the name suggests, it'll be one solid conductor and I don't have to worry about that. Okay, I could, I'm just going to show, I'll strip the other wire that I'm going to solder to. This time I'll use wire strippers. This is a 20 gauge wire, so all my slots here in this are labeled, and they're actually doesn't show a 20 gauge slot, and I'll use the closest one to it, which is 18. So the idea is the slot should be just the right size to just cut through the insulation and not mark up your wire. You're trying not to destroy any of those strands of wire so that your conductor diameter stays the same size. Okay, so again, I'm just going to twist these up here to get all the wires kind of combined into what looks like a single conductor. So again, one of the challenges is holding things steady when you're soldering. You often find that it's nice to have a third hand in place to solder with. So I'm going to just put one of my wires in my my electronic vise here that we showed at the beginning. Okay, so this vise, I've just tightened it up to hold that wire. Okay, let me maybe move this into the frame here a little better. Okay, and I have my other wire here that I want to solder these together. Now when you do solder, join these wires together, it's likely that you're not going to want the bare conductor exposed because you're at risk of shorting that conductor out. Maybe it's carrying power, whatever the case may be. Now you could solder it, and we could use black electrical tape to wind around this to put an insulative material on it. But if you haven't discovered heat shrink yet, you'd be very impressed with how heat shrink works. So the only thing is we have to plan for heat shrink in advance. So it comes in various diameters. This I've just picked out a diameter that's appropriate for this wire, and it often comes in long lengths. I've cut off a piece that's about the right length for this, that's going to cover the exposed copper once it's soldered. Okay, so again, I have to plan in advance, put this over my wire, because of course I can't get it over once the wire has been soldered. So let's just slide that on, and let's prepare the wire for soldering. So one of the first things we do, so I'm going to get my solder out here. One of the first things you do when you're soldering wire is we want to tin the wire first. Okay, so to do that, again, I have my nice clean tip here. Let me zoom out just a little bit here. See that I'm keeping that tip clean on my sponge. It's been tinned already, but I also want to tin the wire. So the trick with soldering most people get wrong is you want to melt the solder into the conductor that you're soldering, okay? Not into the tip of the soldering iron, okay? So here I want to heat that wire hot enough that the solder melts into the wire. Sometimes to help this process, it helps to dab a little bit of solder kind of at the joint between the two, helps with heat transfer. Now you'll see the wire is hot enough that my solder is melting into the wire itself. Okay, so let me maybe show that again. I see that solder is melting into the wire without me actually making contact with the soldering iron. Now to get a nice smooth coating on the wire, this takes it's a little bit of a trick, but I find if you get it nice and hot, drag your soldering iron along the length of the wire, and it'll kind of smooth out the solder over the wire. So the wire, you might note, hasn't increased much in diameter. It's just now coated with solder. Okay, maybe a little bit difficult to see in that at that zoom level. Okay, so just let me zoom in here a little bit. Okay, so nice coating, fairly nice and smooth. It is a multi-strand conductor, so you're not going to get perfect smoothness on there, because again, remember, we twisted that wire up. Okay, so I'll do the same to the other wire. Let me just stick it in my vise here. It's you need that support for the wire, because you have to put a little bit of pressure on the wire to get that heat transfer. Again, let me just dab a little solder there to get the heat transferring, and then I can melt my solder into my wire. And what I'm looking for is to have a wire that's completely coated and not really any copper showing. Okay, so with a good amount of tin applied to both of these solder joints, now I want to join them together. Okay, so I'm going to actually clip the ends of these a little bit just to clean them up. I don't need them quite this long to join two wires of this size together. Probably only need half a centimeter so of exposed copper there. So clean those up, hold the two wires together, and then if I just rub my soldering iron back and forth to try to get a smooth layer, essentially when you're done, you should see that the two conductors look like one single conductor. Okay, so I turn it around, look kind of at all sides, and that looks like I have a nice solid connection. Good indicator of a good solder joint is that the solder is shiny once it's cool. And to get that shininess, I need to have got everything sufficiently hot, and I need to make sure that the components you're soldering together don't move until the solder is cool. If you move them, you can get what's known as a cold solder joint. I'm going to take my heat shrink now, and I'm going to bring it up over that exposed joint. Okay, let me just stick it back into the vise here. And as the name suggests, the heat shrink can be shrunk through the application of heat. So what I've got here, just gonna get, didn't show this part of my soldering kit. I've just got a Mastercraft heat gun. I'm gonna just turn this on, apply some heat. And we notice that the heat shrunk has shrunk and sealed that joint. So I have a nice sealed connection that's well insulated. Okay, let's move on to soldering some printed circuit boards connections. So you'll recall that back in our Altium designer workshop or class, or lab, I guess, we came up with a microphone amplifier, and I might have shown you this one, which was a little bit more advanced version of the amplifier that had a series of LEDs as well, and actually had audio outputs to go back to, if these were connected to headphones, you could provide a left and right channel of audio. Okay, and this is a board that we designed as part of our how-to workshop series, and that looks like this. Or if we flip it over, we can see those components, much like the components that we were working with in our Altium design. Okay, so I've got one of these boards here. So let's just put this circuit board in my vise here to hold in place. Okay, let's zoom in so we can have a little bit of a closer look. So this is just the blank circuit board without any of the components on it yet. So I'm going to need to put those components on there. And you can see the various what we call reference designators, as we talked about in Altium. Might be a little bit difficult for you to read, but here's R19, R18, C10, and so on. Here's the op amp that we use, U1, and we see some other connections. Right. So going back to our design, we need to find the right components to put in each of those spots. Right. So there's the U1. It shows U1 as having components A, B, C, and it actually has a D because there's actually 4 op amps in a single package here, but they're all part of that single integrated circuit package that's shown as the gray block here on the right of the screen. Okay, and again, we see all the other various components on the board. Current limiting resistors in series with our LEDs. This is a serial to kind of parallel port device that allows us to use 2 serial lines to control 16 digital outputs. Okay, so going back to the circuit board here again that we want to assemble with the components, I typically recommend starting with kind of your lowest profile or shortest components and working your way to bigger components. Our integrated circuit packages that are shown here as U1 and over here is U2, a little bit hard to see here. Those are both fairly low profile, and I like to start with the integrated circuit packages because they kind of act as a reference and can sometimes be difficult to get at the pins to solder those when you start getting other components put in place. So here's a single one of the op amps, an MCP604. Probably difficult to see in this frame, but this comes in a ribbon. There's a strip of however many you order come in a ribbon, and often it's handy to keep them in their packaging if you're ordering them from DigiKey or whoever, so you can more easily identify them. I'm not sure if with this camera if we can see, but you could see should be able to see the name of that chip on the package. Let me move over to my microscope here and we'll have a little bit closer look. So here we are with looking at that op amp again under the microscope. Still a little bit hard to see because this package still has a plastic coating, so if we peel this package coating or the cover off this package here, okay, now you can probably see the name, maybe MCP604. Tip it a little bit to the, there we go. We see that's the op amp that we need. I'm going to take this out of the package here with my tweezers. Okay, and I need to place this in the correct location on the printed circuit board. Okay, let me just slide my board a little bit so we see U1 shown here on the circuit board. See the reference designator. We also see right there at the end of my tweezers, we see a white dot. That white dot is denoting pin 1 of my op amp. Right? So when I put my op amp in place, I want that round dot that denotes pin 1 to be on the right corner. If I do this wrong, nothing's going to work, and I'm probably going to destroy my device. Just going to return to this camera that has a little wider view because it's a bit challenging to see what's going on under the microscope. Okay, so I've got the package in place. You know, I want to have it centered over the each of the pads here, you know, centered lengthwise and or vertically and horizontally, but I'm actually going to take it off for a second. I find that one of the easiest ways to start soldering a integrated circuit package like this is to apply some solder to one of the pads on the corner to get you started. Again, we'll remember here that I'm aiming to melt the solder into the pad. Okay, I don't know if you hear me here, but in the background here I'm cleaning my solder tip on my sponge here again, right? So always keeping that tip cleaned and re-tinning that tip if you find the tip gets dull. Okay, so now I'm going to touch on the pad that I want solder to go to, and note the solder melting into the pad. I didn't melt it into the tip. Okay, the other thing to note is these the copper on this printed circuit board is glued down. I have to make sure I don't apply heat for too long, otherwise the glue is going to start to lift and the copper can come off my board. So this is one of the things we have to be careful of when soldering a printed circuit board. Okay, with my solder on there, I get ready with my chip, in this case my op amp. I reheat my solder and I'll just bring my chip into place. Oops, and in this case I've got it flipped around here, making sure pin 1 is in the right corner. Okay, reheat my solder, bring it into place. Okay, once I've as you'll note, until I've kind of got one corner soldered, it's hard to kind of get that device to stay in place. I'm just going to move it centered a little bit better. Okay, so there I am. I've got one corner centered. It still, you know, can move a little bit if I push it. So, and if I need to do a little bit of alignment, I can. And I would then just maybe solder one of the other corners once I'm happy with the position. And again, I can use my tweezers or use my hand just to get it rotated just right. Okay, so once I have two of the pad soldered, now we'll notice it's not going to go anywhere. So now I can quickly go along And here you'll note, back when we were talking about choice of components for designing our printed circuit board, I talked about the importance of thinking about the spacing between the pins, right? You don't want, if you plan on building this yourself, you don't want pins that are too close together, otherwise it's going to be extremely challenging to solder by hand. Okay, so here I just go along, I heat, and I'm trying to heat both the pin of the chip and the pad that it's on. So I'm trying to get my soldering tip to touch both at once. Notice I drag my tip away along the leg to try to smooth out the solder. Okay, and I'll do that for each of the pins. I'm just going to rotate this so I can get at the other side a little bit more easily here. Bring this into the frame a little better, and I'll go along and solder the other legs. Again, heating the leg and the pad that the component is sitting on, so both devices, both pieces that are going to form the joint are getting hot enough to accept and make the solder melt. So the solder should be melting both into the pad that that pin is sitting on and the pin itself. Okay, let's now I've got that soldered. Let's go back here again and see if we can have a look under the microscope to see what that looks like. Okay, here we are under the microscope. We can probably change what we're focused on here. Let's try to bring one of the pins, solder joints, into focus. This camera's a little bit slow to respond here. Okay, so we can see that in every case it looks like the solder has flowed well into both the pin and the pad on the circuit board. This second pin down, I might question, does it, not sure if it flowed into the pin well. Maybe I'll reheat that one a little bit. Okay. I'll even apply a little bit more solder. I don't want huge blobs of solder, right? It should be, I really just need enough solder to join the two conductors together. Okay, you'll note that all the solder, nice smooth finish, nice and shiny, all the characteristics of a good solder connection. Okay, so normally I would, like I said, put all of my low profile integrated circuit packages on the board. I'm just going to do the op amp just because I want to proceed on to showing how to solder some of these passive components, passive, resistors, capacitors, etc. Okay, so here it becomes important to make sure that you know what package your component came from, particularly for capacitors, because they're often not labeled with their capacitance value. So when you order those, they'll come in the package that's labeled. Make sure you keep track of those. So I've cut off a capacitor. I've taken it out of its long strip and just taken one here. I'm going to try to take it out of its package. Okay, so it has a plastic layer holding it in there. If I peel this layer away, I can get access to the capacitor. Okay, so there's my capacitor. You'll note there's no marking on that capacitor. I know that this is a 0.1 microfarad capacitor because it came out of that package. Okay, I'm just going to dump it out on the circuit board. Okay, this is a 0805 package size capacitor. These ones are reasonable to solder by hand, but again, this is where the choice of component is important so that you make sure it's something that you can solder. So I know, if going back to my schematic here, I know that my capacitor C3 here on my op amp is a 0.1 microfarad capacitor. So on my board I see here is C3. Okay, so again, what I find helpful when soldering these components is to apply some solder to the pad itself, just one of them, kind of like I did with the integrated circuit package. So I've got solder on one of the pads where that capacitor is supposed to go. I grab my capacitor, reheat the solder, and slide that capacitor into place. Okay, I'm kind of picky. I like to make sure my capacitors are nice and square to the edges of the board, and of course square to the pad, so that capacitor is meant to be horizontal. I try to place it nice and horizontal. Okay, with one side soldered, now I can heat both the capacitor and the pad and melt my solder into it. Okay, again, note I'm not holding the solder there a long time, and I'm not putting a lot of solder on, and you'll notice a nice shiny finish on the solder, and no big protrusions from the solder, nice and smooth finish. Okay, and I could do the same thing with a resistor. I've got resistors. You see I've left these in a little bit longer strip here. Resistors generally have, at least in this size, this is 0805, they generally have the value printed on them. As you get into smaller size resistors, they may not have the value on them. So again, then it becomes important to keep track of the package that they came from. So this one, I'm not sure if you can tell here, but this says 271. So 27 times 10 to the 1. So this is a 270 ohm resistor. Okay, I'm just going to dump that out on the board. And I know that all of these current limiting resistors for the LEDs around here are 270 ohm. So I'm just going to bring this over here. I'm going to use the same technique. I'm going to apply some solder to one half of the one of the two pads. I'm going to bring the resistor into place, and here the resistor is not actually lined up to be parallel to the edges. I've placed these resistors in kind of a circular pattern just because of the layout of the LEDs. So I've tried to line it up square to the pads. Okay, heat both the pad and the contact on the end of the resistor, melt my solder into there, and I see a nice shiny smooth solder connection. Okay, so that's kind of it for surface mount components. These are surface mount because the pins don't go through the holes in the board, right? So fairly easy. But let's have a look at a couple of through-hole type components. So the through-hole components that are used on this board are the headers. So these are going to go into these holes to allow the board to plug in to the mating board, right? In our case, this would plug into our UMB dev board if we wanted, right? And I've got the LEDs, which are also through hole. They have leads on them to go through the holes, and we'll come back to those in a second because I'm going to start with the header. Okay, so this, one of the first things is to make sure I've got the header in the right way. So that black end's meant to sit on the surface of the circuit board, and of course I want the longer length to be on the bottom of this board because that's how it's going to plug into the mating board, right? And then this way my pins just barely come through the surface on the other side, just enough for me to solder. So I'm going to put this in to my vise here again, and this is where it becomes a bit of a challenge, because if I let go of that, it just falls out, right? So this is where again it can be handy to have another hand to hold things in place. Okay, so what I might do for something like this is I might actually take it out of the my vise to begin with. Okay, just lay it on a surface so that the pins are pushing on the surface, and so that they don't fall out. And I may start by just soldering one pin again. Okay, so let me solder one pin, heating both the pad and the pin. Now, okay, so that's it's now going to hold that connector in place. But if I look at the connector here, I'll see that it's not nice and square to the board. So what I might need to do here is, and again this gets tricky, you try not to burn yourself, is with the solder just on that one pin, reheat that pin, and then line up your connector. Okay, and I know my camera work's not very good here, but now you can see that the header is nice and aligned. See if that can focus on this, right? It's nice and right angles to the surface of the board, and we'll see that the header is the plastic stop on the header is down tight to the surface of the board. Okay, so with that in place, I'll stick the board back in my vise. Try to focus again here, and don't touch the pin that I've already soldered, because that's going to fall out again. So I'll start at the other end, apply some solder. So now it's held by two pins, and I can go along and solder it. Now you may note that I have to hold the soldering iron on these a little bit longer, because the pins are physically bigger. They're sinking more of the heat away from the soldering iron tip, so it takes longer to get it hot enough to melt the solder. Okay, but I can kind of test, see if my solder melts, right? Test, yeah, see, and I can get a sense of when it's hot enough. Again, in my background here, I'm keeping the tip of my soldering iron clean, so it looks nice and polished and shiny. Okay, now let's move on to another surface mount, through hole component whose pins go through the hole. Here we have an LED. You might recall, or you might have seen documentation, that the longer pin of the LED is the cathode, or the pin that needs to connect to the positive. And you'll notice that the printing, or the silk screen on this board, is labeling the positive pin. So I'm going to stick this in this hole. Make sure you put it on the correct side of the board, right? This is the side of the board that's going to be, we want to be visible, so that's the side we want the LEDs on. So with that LED in place, again, now it becomes a challenge. How do I solder that LED without it falling out? One thing I can do is I can take the pins and bend them a bit. This is common for through hole components, so that now it can't fall out. Okay, so now what I might do is apply some solder to just one of my pads to begin with. Okay, nice shiny connection. I take it out of my vise here, check to see if my LED is at nice right angles to my board surface. In fact, it isn't. And this LED actually doesn't fit in the board very well. It doesn't sit down flat. I would prefer to have them sitting down flat, but anyway, again here I can reheat the solder on the back of the board here, and with my other hand I can straighten up the LED, so I get my LED nice nice right angles to the surface. And these, because they're sticking up out of the board a little bit, I can even bend it a little bit to get it in the position I want. Okay, with one of the joints, solder joints formed, and the LED where I want it, I can solder my other side of my LED. Okay, now clearly we don't want these long pins sticking out from the LED, so and this is common for through-hole components, whether it's LEDs or resistors or capacitors that have leads on them to stick through the board. So here I go and I clip those off, and I just leave the basically just above the solder, maybe about I don't know, millimeter, half a millimeter of the lead left. Okay, clip those off, and now I've got a nice finish connection where that LED was soldered to the board. You can see right here, oops, right there and there, where those leads were sticking through. Okay, so there are more advanced soldering methods. Like I said maybe back in the beginning, there is a such thing as solder paste. You can get stencils for the board that would go over the surface of the board with just the locations where there is supposed to be solder, basically all these little silver pads, and you can squeegee the paste through that stencil so that when you peel the stencil off, you only have solder on the pads. Then you can place all your components, and you can put it into an oven to cause this solder paste to liquefy, and then when you take it out of the oven, or the oven cools down, it would harden, and everything would be kind of soldered simultaneously. Okay, so that is a potential technique. Other technique for soldering. You can get into some other techniques for soldering integrated circuit chips that are multi-pin, kind of more quickly as well, but we won't look at those too much here. What I want to look at is desoldering. Okay, often we find we want to, maybe we messed something up, maybe we fried a component on the board, and we want to remove it from the board. So I'm going to look at a couple of simple desoldering techniques. The first one I'm going to look at is using a device called a solder sucker. Okay, so this device here, you can see the whole length of it. It is a spring-loaded suction device. When I push this in, it locks in a plunger. Okay, and when I push this button, the plunger pops out. It sucks air into this this Teflon tipped end of the solder sucker, and it sucks up solder with it if you have solder, hot solder near it. Okay, so let's try this on the LED. One thing that's is maybe counterintuitive when you're trying to desolder something, especially if it's been soldered for a while, one of the things that's often helpful is to actually add a little bit of new solder. Right? It just helps with the heat conduction. Okay, so I'm going to add some solder here. In the background, I'm going to load my solder sucker so I have my spring compressed, ready to suck. Okay, heat this up. I need to make sure it's heated well, so it's heated through the board. Bring my solder sucker, press my button, and you may not be able to tell, but most of the solder sucked out of that hole. I can do the same for the other one here. So I added a little bit solder, gives me good heat conduction, and suck that up. Okay, so now my LED is almost loose. I might have to apply just a little bit of heat to the pins to get it to pull out of the board. Okay, so that's desoldering through-hole components. Surface mount components, if they're just 2-pin, you can probably heat them quickly enough move back and forth between pins to heat them so you can remove them, or you might even be able to heat both sides of the pin at the same time by laying your soldering iron kind of sideways. You might note that when I'm trying to get heat quickly to the board, I'll kind of use the side of my soldering iron to transfer that heat. Okay, so here I could I'll try to heat both ends at the same time, but a more reliable method might be to use solder wick or solder braid. Right, solder braid is kind of like it sounds, is a braided conductor, but it has the flux impregnated into the braid, so it's very solder wants to get sucked into this braid. So when I take this braid and I heat the solder joint through the braid, the solder gets sucked into it, and actually you'll see that I had enough heat on that resistor that the other side came free as well, right? And you'll see that the solder sucked into that braid, and again, that's due to the flux in there, and you have a lot of surface area, so it kind of sucks up that solder. Okay, I'm just going to heat the other side of where that resistor was and clean up the pads. Okay, so as we use the solder braid, I like to cut off the part that has solder sucked into it. It's no longer going to work well for sucking solder up. So maybe we want to remove this op amp from the board. So I could go and try to remove the solder with the solder braid 1 or 2 pins at a time, but it's hard to get it to release. There's always a little bit of solder you won't get off, and it can be hard to remove the chip. So I'm going to show you a bit of a way to cheat. So I'm going to go back to my heat gun that we used to melt or shrink the heat shrink, right? This is just a standard Mastercraft heat gun. Now this you have to be careful with, because it does get very, very hot, and we don't want to melt any plastic things on the board. Maybe you might have plastic connectors, so you're not going to be able to hear me here, but I'm going to turn this on, and I'm going to just I can both watch for the solder to start to get liquefy, and I'm going to test with my tweezers here to see if the chip is free to move. And I don't want to pull on the chip hard, because I don't want to rip the traces off the board. So I'm just testing gently to see when that chip moves, and then I can hopefully remove the whole chip at once. And there you go. We removed the whole chip at once, and with the chip removed, I could go and use my solder braid to clean up the pads where that chip was, to make it get it ready for the next device. Now, I don't know if you've noticed here, but in the process of heating that with the heat gun, you'll notice I melted my header. Okay, so that's just an example that you have to be careful using the heat gun in this way. And true desoldering tools have a heat gun that has a shroud around the tip that you can kind of control where that heat is flowing, so that you can keep it away from kind of your sensitive components, or those components that may not be tolerant to that heat. Okay, so that's everything I wanted to look at in this lecture. Again, feel free to go out and purchase yourself some of these tools. You can get them pretty inexpensively at places like Canadian Tire, or even Princess Auto, or there's plenty of resources online, Amazon, wherever.